Hello, everyone. Welcome back to SAT Math Question of the Day. So, here's our question of the day. Please read it, try it yourself, pause it, come back, and we will go over it. Okay, here we have a graph. They call it a scatter plot of cooling coffee, temperature, and time. The scatter plot shows the temperatures Y in degrees Celsius of a cup of coffee cooling at 22 degrees. Cooling in a 22 degrees centigrade room at 5-minute intervals. If X represents the time in minutes, since the coffee had a temperature of 92 degrees, which of the following can be used to predict the temperature of the coffee from 0 to 60? So, yesterday, Seth noted that the graph looked like it was an exponential going up, so the
It's a different problem.
Yeah. So let's first look at the form. I mean, it looks like an exponential going down, doesn't it? Looks has an exponential curve to it. So, there is only, these are exponential, these are not. These are linear. And the graph is not linear. See, there's no exponent in the x on these. I won't cross them out as much. So these are out. So now it's a question of these. So, each of these have a starting value of 92. When x is 0, this is 92. And when x is 0, this is 92. But this is the one. Yeah, that's the one, right?
No. No way.
What? Oh,
No
yeah,
way.
right. Oh, my God.
Again, it's
Oh my God, I am so stupid. Oh, I am so stupid. It's this one because it zeroes out at 22. Oh my God. Oh,
Yeah.
I did it too fast. Oh, that was really bad. I may have caught it myself when in checking it because I may have asked myself, okay, what is going on with this? Is this possible? But I really blew this one. Wow, that was bad.
Let's see. The exponential decay means you have some fraction. In this example, it's 925 thousandths, and the fraction is less than 1.
Right.
And then the thing is, if you take a fraction, take a pi, right? And you slice away, like one, how much? 75ths, 70, you slice away 75 hundredths, you slice away 25 thousandths of the pie shrinks by a certain factor. And just take slicing away by the same factor, it gets smaller and smaller. A better exponent to visualize is a half. So that's a half, like half of a pie. Take half of a half, and we get a quarter of a pie. Take diminish it by half 3 times, and what you get is an eighth of a pie. And keep going down. 1/2 to the t, 2 raised to the tth power is big as t gets larger. So this approaches 0. And any exponential, exponent f with power t, as t gets larger and larger, f to the t gets smaller and goes down to 0.
Right.
Well, and that's characteristic of this formula. But if we, here we have a behavior that approaches the constant temperature, which is room temperature, and it's not 0.
Right. So you have to add. You
right?
have to
But
add
the way you
22 to
get
the exponential.
a function with this behavior where it approaches a non-zero value from a function that does approach zero is you simply add whatever this is,
Yeah.
right? And
Right.
that's what this is.
Yeah. Wow. I really made that mistake there.
Yeah.
Again, I don't know what I would have done on checking. It's possible I would have caught that, but because I would have checked. But Seth caught me.
Well, okay. What's the lesson? What's the lesson? The lesson is exponentials compared with exponentials to which you've added a constant.
Right. Exponential curves that don't go to zero
Yeah,
you have to add the
exponential decaying curves.
right exponential decaying curves that decay, but they don't decay to zero. They decay to a non-zero number. You have
Yeah.
to add that non-zero number onto the exponential curve because the exponential curve vanishes.
So
The value of
what
the
we did
exponential
do is we
vanishes.
covered two parts to plotting of of an exponential plotting of an exponential function. So here are the axes. We plot it for positive or zero x-axis, and let's see. I want my axes here, and then let's see. So our function is a f to the x plus b.
Yeah.
Okay. When x is zero, we get a fraction raised to the 0th power plus b. Well, any fraction, non-zero value raised to the 0th power is kind of by definition 1.
Yep.
That's because when you multiply, and you don't do any at all, you want 1. 1 is the multiplicative identity. 1 is something you can multiply by without changing it. So it starts out with this unchanging unit, right? If you multiply, and then look at the pattern. If you're supposed to have, you have 8. No, well, anyway, take 8, take the square root, take the
square.
Yeah, multiply it down one to a half. The square root of 8. Now the cube root of 8 is 2. Keep taking smaller and smaller powers of 8. You get little numbers, so you get down to 1.
Okay.
So anyway.
So
okay. The thing is, we both let's erase that. The point is, if you multiply the exponent is motivated by taking a value called the exponent and multiplying it with itself a multiple number of times. If you don't and retain the product. So if you multiply retaining the product and you don't multiply it at all, you should have a 1. Because if you multiply it on once, you want to get f. Multiplying by f, multiply it once, you have to start with 1 for that to happen.
The bottom line is
exponential of 0
anything to the 0th power is
always 1.
Right.
So
anything, this is the word anything.
Yeah.
Anything to the 0th power is 1.
Yeah. So if you're plotting this level is a plus b. And then when the fraction is less than 1, we're talking about exponential diminution. Right. Multiply a fractional number less than 1, positive numbers less than 1, lots and lots of times, you get down to 0.
Right.
And so this term goes down to 0 and you have b left.
Right.
And so you have, well, we call this an asymptote whose
Yep.
height is b, and the exponential curve kind of, it starts at here, right? And it smoothly diminishes down like that.
Yep. Okay, I think we're done.
So you could plot, it's easy to plot or recognize the plot of these exponential diminutions with hardly any calculations.
Yes, absolutely. If you, yeah. Okay.
Now, what's going on? What's going on physically? First of all, 90 degrees of coffee. If you spill that, you get seriously injured.
Of course.
Yeah. Room temperatures. How much is room temperature? So it's in the 30s, like low 30s.
22.
22.
Centigrade.
Wow.
Centigrade. This is centigrade.
Oh, yes, that is. So 22 is moderate room temperature. Body temperature. What's body temperature? It's
in
around
centigrade,
the 30s.
I'm not sure. Yeah, somewhere in the 30s.
Around 30s.
Yeah, somewhere in the 30s.
And here we have 90. That's all, boiling. Boiling of water is 100 degrees Celsius.
Right.
So this is a coffee that they sued McDonald's over.
Yeah.
They don't serve coffee like this unless they want to get sued or injure somebody.
Right. Yeah.
And so how long did it take for the coffee to maybe drinkable temperature would be about 30, 40 degrees.
Right.
It takes 20 minutes.
Yeah, but you could drink with a spoon. You could pull the spoon and blow.
Yeah. The only way to drink is with a spoon. You take a sip, you blow on it, cool it off.
Yeah. You could also stir it. You could stir the coffee and that'll cool it off. So there are ways to drink your coffee in less than 20 minutes. Okay, Seth, I think we're done.
But also add ice or cold creamer.
Right, but not in this problem. Okay, so let's clear all drawings. Let us answer the question, and let us see if Khan also says that's the answer, and let's do step by step. There are probably not going to be a lot of steps. Oh wow, 5, but you do it a little faster than 5. Okay, since we're looking, let's make this bigger. Okay. Since the graph shows an exponential trend with an upward shift, okay, we are looking for an exponential in that form. So Seth was right. Yes, exactly. So annotate. Yeah, this is exactly what Seth said at the very end when he did his stuff up, when he talked about the stuff up here. Okay. Now A is greater than 0, B is greater than 0, B is less than 1. This function is decreasing. Exponent represents exponential decay, exactly what we talked about, especially Seth. We can eliminate the linear choices. Okay, that was good. I'm glad we did that. I'm glad they did that. Thinking about the situation, this is the physics of the situation. It has a horizontal asymptote, exactly what Seth said. Okay, on the other hand, the graph there has a horizontal asymptote, y is 22, which implies that it reaches 22. So that is the best model. They use the word best, the important best model, because you're with these questions that are scatter plots, you're only looking for the best answer, not the final, not the absolute answer, the best answer. And then you graph the thing, and then that's it. So, okay. I guess that's it, right?
That's it.
Okay, so we'll introduce ourselves. I don't know what this line is doing. I'm sorry about that line. If it's on the screen, I see an annoying line there. But we will continue anyway. This is Seth. He is Seth Chaiken. He's a PhD in math from MIT and a professor emeritus University of Albany in New York. He's retired now, and he is helping. We are doing this together. I'm his brother, Joel. I have a PhD in mechanical engineering. And we try to offer different approaches in doing these SAT math questions. And the approach we advise is going to Khan Academy and taking one of their classes. They have a digital SAT class and a non-digital SAT class. Choose the one that you think you'll be taking. Please like us, dislike our videos, give us comments, and If you have any SAT math questions, email them to us at satmathquestionoftheday@gmail.com. And today's Wednesday, so tomorrow's Throwback Thursday. So hopefully we'll meet tomorrow and we'll do a question not only from the modern SAT post-2016, but an SAT from about 20 years ago where the SAT had a slightly different feel to it. Okay, that's it, Seth. We're done?
That's it. Yeah, we're done.
We're done. Okay, everyone. Have a great day. Bye.